All right, it says we're recording. So we'll share my screen, and so today is an exciting day. Now my notes are mislabeled chapter 18, but this is really chapter 20. And okay.
So will be the homework be chapter 22?
Chapter 20, yes. So yeah, we're jumping up to chapter 20 now. So we're talking about hypothesis tests for a mean where standard deviation is either known or unknown. Okay? And so this whole idea of whether it's known or unknown is very important. In fact, maybe I should change it to known, unknown. Okay? So rules for the hypothesis test for the mean. It must come from a simple random sample. Must be independent. Your data should be normally distributed with no outliers, and your n should be greater than or equal to 30. We can get away with smaller samples, but it needs to say that it's normally distributed if it's a smaller sample. Okay? Now, the first question, well, I don't know if this is the first question, but when you're trying to decide whether to use which hypothesis test, this is what that should say. The question you're going to ask yourself is, do I know the population standard deviation? If the answer is yes, then you're going to use a z-score. If the answer is no, then we're going to use a t-score. Now, and you'll notice here, my formulas are a little bit on the small side, okay? The difference between the z and the t is both numerators are x bar minus mu, okay? The difference is the denominator. With the z-score, you use sigma. With the t-score, you use s. And in both cases, we're dividing it by the square root of n. Okay? Now, a couple things I should probably mention. So the t distribution looks a lot like the z distribution. It's a bell curve. Okay? Now I've got here a
Mr. Bennett, does the S in that case, would that just be your standard deviation, your sample then?
Correct. Yeah.
Okay.
So we're going to use our sample standard deviation because we don't know the population standard deviation. Now, if I were to compare, let's pick, say, green here, your t distribution as opposed to a normal distribution, your S is generally going to be a little bit larger than your N, and so it's going to also be a bell-shaped curve, but your tails are going to be bigger, okay? So in this case, the green would represent your t distribution, and the red would represent the z distribution. Z distribution, okay? Oh, that's hard to read, okay? So, so when we're doing hypothesis tests for means in this chapter, we're going to mostly concentrate on the t distribution because it's the new distribution. And I guess I should also mention the chart, okay? So remember here, you've got your normal distribution and it measures area to the left. With your t distribution, it measures your area to the right, okay? Now, one of the interesting things about it is, so this chart is going to be very different from your z chart, okay? So for one thing, you're not going to get exact values. And another thing about the t distribution is you're going to have something called degrees of freedom. I've abbreviated it DF here, degrees of freedom. So your degrees of freedom, I should add that on here. Maybe I'll do it there. Degrees of freedom equals n, your sample size, minus 1. Okay? Yeah. So we'll talk about, so p-values, we'll talk about that in a little bit. And they're kind of a pain to do with the chart. All right, let me go back to my notes. Now, what I'd like to do is do some examples, and these could be either a z distribution or a t distribution. And so I'm going to do some examples here, and I want you guys to be able to tell me which distribution I'm supposed to use. And so we're going to go through the 8 steps just like normal. And so let's just start here, okay? All right, so the mean SAT scores, SAT math scores in 2007 was 515 with a standard deviation of 114. An educational psychologist believes that 4 years of English courses in high school help students score better on math. Psychologist obtains a simple random sample of 40 high school students with at least 4 years of English and finds their math scores of 540. Use alpha equals 0.05. Find out if the psychologist's beliefs are correct, okay? Excuse me. So what is the first step that we're supposed to do when we're doing this?
Write down your numbers.
List all your numbers, okay? All right, and I think I wrote that down there. Find all the values. Okay, so what are all the values here that we're supposed to find? So mean scores SAT was 515. What's 515?
Your mu.
Your mu. That's your, so you're saying that's population? Okay.
Correct.
And a standard deviation of 114, what is that?
Sigma.
Sigma, because that's, yeah, that also comes from the population. It doesn't say it comes from the population. You have to determine that, okay? Psychologist obtains a random sample of 40. What's 40?
N.
40 is your N. And I've got a math score of 540. What's that?
X bar.
That's your X bar. Well done. Okay. So I found those mu, sigma, and X bar. I've got my alpha 0.05. Okay. So the next question is this quantitative or categorical data?
It's quantitative.
Okay. Got all my answers here if I just don't give them away. Step number 3 is what?
Reject or accept the.
No, you skipped a bunch of steps there.
I'm
And
sorry.
you're using the A word. We're going to have to get some soap
did
and
not.
wash out your mouth. You know that.
Make your hypothesis.
Okay. What's our hypothesis?
Your ho would be 515, and your H1 would be your mu is greater than 515.
Okay. You didn't use mu on the null, but I'm glad you got that right. Okay. All right. So we're good there. Step number 4 is what?
Pick a test.
Pick the test. Okay. So we know it's quantitative. We know we're using mu. The question is, am I going to be using a z-score or a t-score on this one?
Z.
Z because
You know your standard deviation of
we
your
know the
mu.
population standard deviation. We know our sigma. Okay. So I'm going to be using a z-test. Okay. So as I plug it in here, so I'm using the z equals sigma. So 540 minus 515 over 114 over the square root of 40 gives me a z-score of 1.39. So what's my next step?
Finding the p-value.
Okay. Find your p-value using the chart. Hopefully, so I got a 1.39, not this chart, 1.39 will be the last column, 1.39. So I got 0.9015. Oh, that's not right.
You were at 1.2.
Oh, I'm on the wrong level. Okay, thank you. 1.39, 0.9177. So that gives me the area of 0.0823. Now, do I have to double it?
No, because it's a one tail.
No, because it's a one-tailed test. Very good. Okay. All right. So then, reject or do not reject?
Do not reject.
Do not reject because 0.08 is greater than 0.05. So do not reject. We're comparing it with our alpha. All right. So our conclusion. So we need to find out if the psychologist's beliefs are correct. So we're going to pick on Janie because I want to make sure that she's got the conclusion down.
Oh man, I always get these ones.
I know, that's why I picked it, because I wanted you to do well. Okay? So we've got all this. We're trying to find out if the psychologist's beliefs are correct. We said we do not reject.
So then it would be that the psychologist's beliefs are correct.
Okay, so let's make sure. Look, before we decide whether we need to believe this, what does the psychologist believe?
They believe that 4 years of English courses in high school with help, students score better on math.
Okay. So essentially what we're saying, so one way to think about this is the null hypothesis says 4 years of English, excuse me, sorry about that, does not improve your scores, whereas the alternative says it does improve your scores. So we did not reject the null. So does 4 years of English help?
No, I guess.
Yeah, so no is a little bit strong, but it's along the right track, okay? So we would say there is not enough evidence that English helps with your math scores.
Okay.
Does that make sense? So you did good on that one, Janie.
Thanks.
Okay. So, yeah. Now, so here's the tricky thing. Think about this for a minute. We got 515. So normally people should get 515. They did get better scores, 540. Wouldn't you say 540 is better than 515? Under normal circumstances, you would so you would say 540 is greater than 515, but the problem is my standard deviation is so large that we're saying that, well, that's only 1.39 standard deviations away, and that's going to happen about 8% of the time, and because it happens 8% of the time and not less than 5% of the time, we're saying that there's not a significant difference. Okay. So that can be a little tricky, but yeah. So so does that make sense?
Yes.
Easton's the only one to be willing to take a stand on that. How about you, Janie? Are you good with it?
Yeah, that makes sense to me.
Okay. All right, so let's do another one here. I almost feel like I shouldn't. I know I have the answers on here, but maybe I shouldn't. I'll just do this. We won't look at them. Okay. All right. CDC says that the mean cigarette smoked per day by smokers is 18.1. We obtain a random sample of 40 retired smokers to see if they smoke less than CDC numbers. The data results in a mean of 16.8 and a standard deviation of 4.7. Use alpha equals 0.10 to find out if retired smokers smoke less. Okay, what's our first step?
List all the numbers.
List all the numbers. Okay, well done. Now, Seth, you've been awfully quiet, and so has Bridger. Bridger never talks, though. Bridger, can you talk? All semester long, he's never told me why he can't talk. Does he not have a microphone?
You got to catch him within the first 45 seconds of him showing up.
Yeah. I don't know when he showed up, though. That's the problem. So, anyway, Bridger, if you just tell me why you can't talk on here, that would be awesome. Seth, though, okay, can you help us find the numbers here? And Seth, you're on mute if you're talking. We can't hear you. Are you there, Seth? Are you hanging out with Bridger or what? All right. Well, we'll go with Allie then. Allie, what can you help us out with here with?
All right, so it looks like the mu is 18.1. The n is 40. The x bar is 16.8, and the sigma is 4.7.
So you think that comes from a population?
Yes.
Well, isn't the 4.7 because you said that the 16.8 came from the sample, right? Doesn't this come from the sample too?
Would you switch the mu and the x bar then?
Nope.
I'm kind of confused on this part then.
Okay. Janie, can you help her out?
So far, I got the same thing she did. So,
Okay. Wes, do you agree with this?
No, instead of sigma, that should be S.
This is S.
So the numbers are right, it was just the labeling that was wrong.
Exactly, but that's what matters.
Okay.
The labeling is what matters, yes.
okay, so what does S mean then? Like, what is that? What is S?
What's the difference between S and sigma?
It's the sample standard instead of the population standard.
Deviation. Yeah, this is your sample. Standard deviation. Whereas up here in this other one, we use sigma because this was the population standard deviation. Okay, if we look at the previous one, we're saying that the mean SAT scores for the population, it doesn't say population, but this is the population. Okay. Down on this one, you clearly noted that was the sample. Well, this is also the sample. And so because it's from the sample, we use S. If it was from the population, we would use sigma. So does that make sense, Allie and Janie?
Yep.
Okay. And then alpha is 0.10. Okay, step number 2.
So it's deciding whether it's quantitative or categorical.
Okay. And I'll let you finish that one off, Easton.
So this would be quantitative.
Okay. Anybody disagree with him on that? Seth, are you back?
Yeah, sorry about that. My mic was.
Okay. Oh, your mic wasn't working. Okay. What's step number 3, Seth?
To figure out your hypothesis, H naught and H1.
Okay, or HA. I pressed A. Either way, it doesn't matter. Okay. Do you know what those are?
Would it be mu equals 18.1 and then mu is, sorry, I'm just reading it real quick again.
That's fine.
Less than 18.1
Why did you say less than?
because they want to see if they smoke less than the CDC numbers.
Right. They're too poor to afford cigarettes, or they're just not as stressed out because they're retired and they can do what they want. They don't need as many cigarettes, right?
Yep.
All right. Step number 4 is what, Janie?
To pick the test.
The test. Okay. And the tests that we have to choose from are Z, T, or chi-square. So what do you think the answer is?
Would it be the Z test?
Why would it be the Z test?
Because we know the. Oh, actually, maybe not. Would it be the T test because we don't know the population standard deviation?
Yeah, I'm asking the questions here, not you. So the T test because?
We don't know the population standard deviation.
Okay, so that was better. That was a statement. That wasn't a question. T-test, we don't know population standard deviation. That is correct. Okay. All right. Okay, so we're using the T-test. And so that means, here, I'll pull down my formula here. So this is the first time. So this is exciting. The first time we get to use our new formula. Okay. Now, actually, I guess I should mention one other thing. Because we're using the T-test, not only are we using that formula, but there's something else we need to mention up here. And that is your degrees of freedom. Now, degrees of freedom isn't stated in the problem directly, but you can figure it out really easily. What would be your degrees of freedom?
39.
39 degrees of freedom. Okay. It's your sample size minus 1. All right. So we're going to show you that's going to play a big role when we do the p-value. Okay. So who wants to tell me what to type in here for the t-test?
So x bar would be equal to, so it would be 16.8 minus 18.1 divided by 4.7 over the square root of 40.
Now, he didn't mention all of the parentheses in here, but when you're typing it in your calculator, these are going to become essential. Okay, so I put the parentheses in and make sure that when you're doing this on your calculator that you're putting the parentheses in. Okay, just the way I did it there. So when we look at our thingamajig here, we get a t-score of negative 1.74935. Okay, so this is equals negative 1.74935 decimal. Okay. All right. So step number 5 is what, Allie?
Find the p-value.
The p-value. Okay. Now, we've never done that on a t-test, so I'm going to help you guys do this. Okay. Now, in order to find the p-value, it's based on your degrees of freedom. Your degrees of freedom equals 39. Okay. Okay, so I've got 39 degrees of freedom, and I've got a t-score of negative 1.74935. Now, I didn't mention, I probably should have mentioned that a little bit sooner. The t-score equation was developed by a guy named William Gossett. He worked for a beer company, and he's the one that came up with this. And he kind of did it with a pseudonym, and he called it the student t-distribution. I don't know why he didn't want to take credit, but anyway, so that's a little bit of background on that. So if we've got our chart here, okay, now this time we're using a t-distribution. Now, one of the things you'll notice here is these values are always positive, okay, and we got a negative value. Well, the nice thing about the t-distribution, usually, I wonder why that's not in my notes, but the t-distribution is symmetric. I think, here, I need to add something on here because I probably should have told you about some of this stuff sooner. I know I do it in my 2040 class. I don't know why I didn't add it here. Nope, wasn't that one. All right, well, okay, I need to find that. I want to add that on there. Okay, but at any rate, your t-distribution looks a lot like your z-distribution. It's a bell curve. You can see I've got the normal curve that's also there. So here's what you're going to do. Okay, so down this column here, you've got your degrees of freedom. So we've got 39 degrees of freedom in this case. Okay, so what you're going to do is you're going to take, so we're going to ignore the negative for a minute, which we're doing. Remember, this is a left-tailed test. Okay, but I've got a value of negative 1.74. So what I want to do is I want to figure out, I'm going to ignore the negative 1.74. So what I'm going to do is I'm going to look on this line here and I'm going to say, where does 1.74 fit? Okay. And so you can see that 1.74 is in between those two numbers. Does that make sense? Okay. So when we go back up to the top of the chart, that means your p-value is going to be in between 2.5% and 5%. And so that's the best you can do with this chart, okay? So all you can do is you can say, in this case, your p-value is in between 0.025 less than p-value less than 0.05. Okay? Now, if my alternative hypothesis was a not equal, I would have to double both of those values. I would say it was in between 0.05 and 0.10. But since I'm doing a one-tailed hypothesis test, my p-value is in between here. Now, so that's all you can do. Okay? Now, step number 6 is what?
Compare the p-value.
Compare to alpha. Now remember, we're using an alpha of 0.10 in this case. Okay? So, is your p-value less than alpha?
Could be equal to.
No.
Well, the biggest it can be is 0.05, right? That's the biggest it could be. Is 0.05 less than 0.10?
Yes. Sorry.
Yes. So, what if my alpha was 0.05? We're still saying our p-value is less than 0.05. I think that's what you were thinking about, right, Wes?
Yeah, I'm sorry. I guess I was looking at it backwards.
You were so used to the alpha of 0.05, you forgot we had an alpha of 0.10. But definitely, yeah. But even if we had a 0.05, we're saying that the p-value is less than 0.05, okay? So the question is, do we reject or not? And I'll let you take that one over, Wes.
We do not reject.
Do you guys agree with Wes?
Wouldn't you reject the null if it's less than alpha?
So Easton, oh, we got a difference of opinion. Easton and West, that means we're going to have a vote. Okay, so here we go. We're going to vote. Okay, so I got my little chat here. Who says we're going to reject? Is Elise here? Do not reject.
Yes, I am. Sorry, I just got here.
All right, well, welcome. We missed you. Okay, so we've got 2 votes in. Oh, somebody took away their vote. Who's voted here? East and Janie West. Oh, are we unanimous? Oh, no, Elise is not unanimous. Do we have 6 people here now? Elise, Allie, Bridger. Oh, Bridger didn't vote. I think Bridger just signs on and then walks away. Prove me wrong, Bridger. 1, 2, 3, 4, 5, 6, 7. So we've had 6 people vote. Okay, and it's 5 to 1. Okay, majority wins. It's correct. We reject the null because the p-value is less than alpha. Okay, so we rejected the null. Okay. So step number 8 is to write the conclusion in English. I'm going to let Ali do that.
So, because we're doing it in English, are we allowed to use the A word by saying we do not accept?
We are never allowed to use the A word ever.
But the A word is English, it's not.
No, yeah, but that's a swear word. The A word is a swear word. We have to get our soap out.
But you said that we're not allowed to write down like we do not.
Yeah, reject or do not reject. You can't use that one either. So here is your, if you want a template here, there is or is not evidence that whatever you're measuring.
Okay, so because.
So there is evidence or there is not evidence.
So there is not evidence that, wait, I have to scroll up to the word. Yeah. There is not evidence that retired smokers smoke less.
Okay, we're going to do another vote.
It's
Okay,
probably
so you
wrong, I'm
said
not
there
very
is
good at this.
there is not evidence that retired smokers smoke less. So here's our other vote. Okay, do you agree with Allie or do you disagree? Or do you not know? Don't know. I guess I should add the third one in here. We'll let you can be honest if you want. Although you won't get, even if you're honest on the test, you'll be wrong if you put don't know. Allie, aren't you going to agree with yourself?
I'm kind of tempted to say don't know.
Lisa's saying don't know. Okay. Oh, we're getting a lot of disagreements there. Okay. Seth, why do you disagree?
I'm not 100% sure, but I'm pretty sure it's because back when at the question it says, sorry, can we go back up to where the question is so I can, just because I think that there is evidence that they do smoke when they're retired because the p-value is less than alpha.
Yeah. Okay, so you disagreeers, you're correct. There is evidence that retired smokers smoke less. Okay? So Allie, here's how you remember. If you do not reject, there is not evidence. If you do reject, there is evidence. So not goes with not.
Okay.
Is that helpful?
Yes.
Okay. All right. Okay, these are hard. I know they're hard, and that's why we do them hopefully over and over and over. Now, by the way, just for fun, go ahead. Did you, Wes? Go ahead.
Can you go back and show us how we got the t-value again, just one more time from that chart?
Yes. Okay, so we got the value. We type it on our calculator. We got negative 1.749. Okay, when you're using the chart, you can ignore the negative. Okay, and the reason why, so essentially, this chart is giving you the area to the right, but if these numbers were all negative, it would give you the area to the left of the negative value. Okay, so degrees of freedom. we've got 39 degrees of freedom. Okay, so because
And
it
how
was,
did we determine the degrees of freedom again?
who remembers that?
-1.
Yeah, it's your sample size minus 1. So we had
Gotcha.
our sample size was 40, so our degrees of freedom is 39. Okay, so 39 means we're going to be looking at this line, only that line. Okay, and so what we're trying to do, in fact, it might be easier to show you this on my Excel because I think, well, I can keep the stuff there. Here we go. So if I go to my t-distribution, okay, let me make it a little bit bigger. Okay, so I've got 39 degrees of freedom. Okay, so I'm looking at this line here, 39 degrees of freedom. Where does 1.74 fit on that line? 1.74 fits in between these two numbers here.
I got you. There was a typo in your notes. That's where I was confused. You were showing that the score was higher than 0.25 and less than 0, so it should be a 0.25. Okay.
Oh,
That's why I was confused. I didn't understand how the p-value could be higher than 0.25 but less than 0.05.
yeah, sorry, there was a typo there. Yeah, it's between 0.05 and 0.025. Yeah, between those two.
I'm better now. I'm sorry.
Oh, no, I didn't mean to confuse you. That would have been confusing. But yeah. Yeah, your p-value is in between 2.5% and 5%. I was wondering why you missed that, but now it makes more sense why you missed that. So it was my fault. Yeah, that should have been 0.025 and 0.05. Yeah, so sorry about that. Okay. Does that make sense to everybody else?
So it makes sense how to find the p-value, but what exactly is its significance and like the steps following it, or are we just finding it to find it?
Okay, so one way to think about it is, you know how with the z-score, let me erase this for a second. Okay. And because the t-score and the z-score look so similar, so essentially here's what happened. We said that the mean cigarette smoked per day, so this is a t-distribution rather than a z, but they're similar looking. So we said that 18.1, that's the number of cigarettes smoked per day. But we only got 16.8. Okay? So if you convert that to a standard normal distribution, what you do is you could change this 18.1 to a 0, and you change this 1.68 to negative 1.74 standard deviations away. Okay? And so what we're trying to do is we're trying to find the area in the white. Okay? And what we said was, well, we don't know what the area in the white is. All we know is the best we can come up with is our p-value. P-value is less than 0.05 and it's greater than 0.025. Okay? Because unlike so with the z distribution, you can get exact values right off the chart. With the t-distribution, you can't get exact values. We're just going to say, oh, well, where does it fit? It fits in between those two numbers. So it's in between 0.05 and 0.025. But you always list the 0.025 first. So this is kind of backwards. But anyway, and so because we rejected the null, because we're using our alpha as 0.10, we rejected the null, there is evidence that retired smokers smoke less. So they smoke less either because, I mean, now the question is, why do they smoke less? Well, maybe they're not as stressed out because they don't have to go to work anymore. Maybe work stresses them out. Or maybe they're so poor because they don't work anymore, they can't afford a cigarette. So they're like, I conserve these. Those would be the two theories that I would come up with. I'd probably go with the former, that they're not as stressed out. Okay? So does that make sense? Okay. All right, we're going to keep going on these because Well, I will tell you that your homework, this says chapter 18, but it's really chapter 20. Your homework for chapter 20 is going to be focused mostly on your t-distribution, but I will tell you this. If you want to get an exact value in Excel, but you can't, you won't be able to do it with the chart, but that's the formula you would use for Excel. Is t dot dist, you'd put in your t-score of negative 1.749, excuse me, 39 degrees of freedom and true, and you would get an exact value of 0.044, which is in between 2.5% and 5%. Okay. All right. Wireless associate. Oh, this one's good. Let me back up a second. Wireless Association says the mean cell phone bill is $50.64. A market researcher believes the cell phone bill is different today, but is unsure if they're higher or lower. The market researcher uses 12 cell phone subscribers and gets the following results. Assuming the population standard deviation is sigma equals $18 and alpha is 0.05, find out if the market researcher's beliefs are correct. So this time we just gave you raw data, okay? So finding all the values, how would we do that? Here, we almost need to put this on a new page. Okay. So how would you find all the values?
N equals 12.
N equals 12. Is that big enough?
For your sample size?
Right.
You would have to calculate because it's quantitative, so it should be more than 40, correct?
More than 30.
30.
Yeah. It doesn't say that it's normally distributed. that can be another problem. So yeah, so technically it's not big enough. But we'll do it anyway. But yeah, technically it's not big enough. Okay.
Will you ever
What
give
else?
us a problem on the test where like it's not big enough, but we still have to calculate it out?
Yeah. I will.
Do we have to state that the sample size isn't big enough then in that case?
So here's the tricky thing. Does it say anywhere here that it's known to be a normal distribution?
No.
No. So this one's not big enough. But if it said it was normally distributed, would it be okay to use 12?
Yes.
Yes. Okay. So the tricky thing on the test that you'll just want to pay attention to is if it's 12 and if it comes from a normal distribution, then it would be okay. But this one does not make that claim. Okay. So 12 is technically not big enough, but I'm still going to make you do it anyway. Okay. All right. What other numbers do we need?
So mu would be 50.64.
Mu equals $50.64. Okay.
Sigma's 1849.
Sigma is $18.49.
Alpha is 0.05.
Alpha equals 0.05.
Then don't you need to calculate X bar?
We need to calculate because we don't know what X bar is, but we can calculate it. Okay. So if you take this and you stick it in Excel, because this is my favorite calculator here, but I got to get rid of the commas. Okay, so we're going to use the other A word, average, which is really the mean. So we got a value of 65.01, so $65 and a penny. Bar equals, and so I'm going to round that, yeah, 4 decimals, or I'll use all 5 there. 65.01417. Okay, so you're going to have to find that out yourself. Just for fun, we could figure out the sample standard deviation, since I've got this here. And I don't know if I'll need it, so that's $25.45. 25.45. 3. If it's a t distribution, I'll need my degrees of freedom. What would my degrees of freedom be?
$11.
It would be 11. So I'm going to put that there just in case. Now, do we know at this point if I'm going to be using a z or a t or a chi-square? Or should we wait till step 3 to figure that out?
We do know that it's going to be a z-score.
Why? Why is it going to be a z?
Because you've got your standard, your population standard deviation.
We've got our sigma. That's exactly right. So because of that, it's going to be a z distribution. Okay. So we could know that, but we'll get that to step 3 anyway. Okay. All right. Step number 2. So I don't really need the degrees of freedom because I'm using a z. Okay. All right. So step number 2.
Determining whether it's categorical or quantitative. Quantitative.
Quantitative. And it is. Janie, it must be your turn. Categorical or quantitative?
Quantitative?
You always do that as a question. You're supposed to be like, it's a statement.
It's quantitative.
That still sounds like a question.
It's quantitative.
That was better. Quantitative. It's quantitative. Okay. All right. Step number 3, Allie, is what?
Reject or accept.
No, you're skipping way too many steps.
We have to write it down. So the null, the null is that H0 equals 50.64. And then the HA would be would it be the 50 point? Wait, no, it'd be 18.45, right? Or are we looking for the population? I'm kind of confused on this one.
Oh, okay, we got to help her out. Who can help her out here? I was going to tell her that she only got half credit for not giving me the thing. But then she was going mu or sigma.
It's mu.
Why is it mu?
Because you want to find out if your population is the same as the sample.
Well, isn't sigma population?
Yeah, but that's the standard deviation. You want to know what your parameter is.
Well, sigma is a parameter.
Yes, sigma is a parameter too. I'm trying to think of the right verbiage.
What are we measuring? Are we measuring, what does sigma represent?
The quantitative data.
Save me, Easton.
Sigma is the standard deviation
Right. Are we
and cell
checking?
phone cost.
Are we doing a standard deviation test on this?
No.
No. We're doing a mean. That's what I was trying to get Wes and Janie and Allie to say. Okay, does that make sense? Allie?
Yes.
Okay. All right. So since the null is mu equals 50.64, what's the alternative?
Wouldn't this one be mu does not equal 60 or 50.64?
Why did you say that?
Because the researcher's unsure if the cost should be higher or lower. He just thinks it's different from that.
Right. Okay. Do you agree with that, Allie?
Yes.
All right, good job. And I like how it was yes, not yes. All right, step number 4, Seth, what is it?
It's a z-test.
It's a z-test. So you're supposed to pick the test, and you said it was a z because
Because we know what sigma is.
we know what sigma is. Okay, and we mentioned that earlier. Okay. All right, so here we go. So we're going to be using this formula here. We won't use any of those numbers though. So z-test. Elise, can you help me plug in all these numbers? Did Elise leave already? Oh, she's here. We can't hear you though, Elise. Okay, Janie, can you help me?
Yeah. So it would be 65.01417 minus minus 50.64 over 18.49 divided by the square root of 12.
Okay, well done. So when we pull that into our fancy dancy calculator here, oh, it doesn't like my space. Let's try that again. So I get 2.69301, okay? Equals 2.69301, okay? Elise, are you back? No, she's not. Whose turn is it now? Seth, it must be your turn. What do we do next?
We compare to alpha.
We need to find the p-value first before we do that.
Yeah, we find it. But
We
after
find
that,
the p-value. Or the p-value. P-value. So how do I do that?
we need to go to our chart.
Okay. We're going to our Z chart, our normal chart, okay?
And find it closest to it.
I forgot what it was. 2.69. 2.69, that'll be the last column. So 0.9964, is that the correct answer?
Yeah. Yeah. Oops.
Do you guys agree with him?
No.
Uh-oh. Easton's throwing down the gauntlet. Why not? Why is that, Easton?
Because that number gives us the area that's left of that value, but we're looking for the two tails.
We have to subtract by 1.
All right. Okay. All right, so we need to subtract that from 1. So 1 minus that equals, let's see, 10 minus 4 is 6. 9 minus 6 is 3. 0, 0. 0.0036. Okay. Now, the question is, do we double it?
Yes.
Yes, because
It's a two-tail test.
you have to double that, and that's a two-tailed test, so that becomes 0.0072. This is a tricky one. Would you get it right, Janie? Would you remember all that?
Wait, what would I remember?
To subtract it from 1 and then double it.
I would remember to subtract the 1, but not to double it.
Okay. But you're going to remember that by Friday.
Oh, we'd hope so.
All right. So now, as Seth said, we're going to compare to our alpha. And step 7 is what, Allie?
Decide whether to reject or not reject.
Okay. And what do you think?
Well, the p-value is significantly smaller than the alpha. So it would be do not reject.
Okay, it sounds like poll question time. Do you guys agree or disagree? Agree, disagree. Only one person's voted. Uh-oh, we're getting some disagrees.
That's nothing new. I'm normally not very correct with these things.
Okay, so let's think about this again. Okay, we're comparing it to alpha. Okay, what's the phrase that pays? Do you remember the phrase that pays, Allie?
No.
Does Wes remember the phrase that pays?
If it's bigger than your alpha, reject the hoe.
If p-value is low,
Oh, if value's low, reject the hoe. That's right.
reject the null hypothesis. So, Allie, is my p-value low?
Yes.
It is low. So therefore, I would reject the hoe or the null. Okay?
Okay.
Is that going to help you? Are you going to remember the phrase that pays?
Yes, now I am.
Okay. All right, so now we've rejected the null. And who do we want to pick on? Elise, can you give me a conclusion?
Yeah, maybe I have to look at the question. So is it we do not agree?
Okay, so remember the template is there is or is not evidence
Or there is
that,
no
and
evidence.
then whatever.
So there is no evidence that. Can I look at the question again? There is no evidence that. There is no evidence that the believer's cell phone bill is higher.
There's not evidence that the cell phone bill is higher. Okay, so that was Elise's conclusion. So it's time for another agree or disagree. Paul. Should I throw in the don't know option? Oh, I'm going with the disagrees. You guys are all just contrarians. Okay, I think we got everybody to vote because Bridger never votes. So, Ali, why do you disagree?
Because you were saying before that like the not goes with the not. So
You're remembering that. That's good.
yes, I'm learning.
Yay. All right. So the not goes with the not, and there's not a not here. So there should not be a not here. So there is evidence that the cell phone bill is higher. Now, the one thing that I like about Elise is she didn't, so some people would just say there's evidence that the cell phone bill is different. Because all we're saying here, remember, we said the person is unsure if it's higher or lower. And so when we did our null hypothesis, we said not equal to. And so some people would like to say not equal to here. But I was proud of Elise for saying higher because there is evidence that the cell phone bill is higher. Okay, not just different. So even if you do a two-sided test, I would rather you said that there's evidence that the cell phone bill is higher or lower, because it could have been lower in the case. But the question is, okay, so remember, Elise, not goes with not. If you do not reject, there is not evidence. But since we did reject, there is evidence. Now the question is it higher or lower, and how do you know? I'll try to get the numbers there.
Because the p-value is less than the alpha.
So the p-value is lower than your alpha, but that doesn't. But the p-value is always positive, and so that doesn't tell you whether it's higher or lower. So yes, the p-value is low. That is correct, but that doesn't tell me if my cell phone bill is higher or lower.
Okay.
What tells me that my cell phone bill is higher or lower? Easton, what do you think?
So we know that the average cell phone bill is higher because X bar is greater than mu.
X bar is $65, and we said it was only $50. So we know that the cell phone bill is higher. It's gone up by almost $14, $15, whatever, 14 and a half. Okay, so based on our X bar, we know that cell phone bills have gone up. Okay, this is hard stuff, huh? Was I correct, Janie, that this is hard stuff?
I mean, yes. Yes.
All right, are you getting it?
Yeah.
Are you studying with Easton? Seems like he's got this stuff down pretty good. Do you wish you were studying with Easton? Maybe that's a better question.
How about Easton just take the test for me?
All right. Yeah, because I know this is hard, but I will tell you this. And I don't know if you guys know each other, and it's kind of a little bit harder in the online environment, but studying with each other helps. Okay. So, all right. Oh, well, actually, that's not a bad question. If we constructed a 95% confidence interval, I want to do one more of these. I'll just do this really quickly since I got the answer there. The lower bound of the confidence interval is $54. The upper bound is $75. Because the null hypothesis is $50 is not in between 54 and 75, there is another reason to reject. Okay? Does that make sense? If we had done a confidence interval instead of a hypothesis test. Now, one other thing I do want to mention here really quickly, because sometimes I'll do this on the test. Okay. What if, well, let me just show you it really quickly on your formula sheet. I also have here, so, okay, so we've got your z-score is here, your t-score is here. You got your other z-score if it's proportional data. We also have confidence interval formulas. So the confidence interval formula works the same way. If you know the population standard deviation, you're going to use the z. If you know the, if you don't know the population standard deviation, you're going to use the t. Now, let me just mention this really quickly. If this is a z, right? Yeah, this is z. If we were using a t distribution, here's how you would use the chart. Okay, we've got 11 degrees of freedom. Okay, sample size is 12, 11 degrees of freedom. Okay, now one way to think about this is if I want 95% confidence interval here in red, how much do I want in the tails?
2.5.
2.5 in each tail. Okay. So the question, so if I'm looking at a confidence interval and I want a 95% confidence interval, I'm going to look in this column with 11 degrees of freedom. Okay. And so that's going to give me 2.201. And so I'm going to use that number, 2.201, rather than the z-score, which is 1.96. Okay. So you can also, remember with the normal distribution, I give you lots of different, well, these are the 4 that you're going to use most often. Okay. But remember, with the t-chart, these are, you could think of these as all, we've got 2.5% in each tail. 2.5 times 2 is 5, and so that would give me 95% in the middle. Okay, so this can also, this chart can also be used to find confidence intervals. Okay. All right, we've only got 10 minutes left. I want to do one more. And maybe we'll go a little bit faster because we're on 10 minutes left. Okay. All right, fun-sized Snicker bars are supposed to weigh 20 grams. The punishment for selling candy bars less than 20 grams is severe, so the manufacturer calibrates it at 20.1. Quality control is concerned about calibration, so she weighs the 11 candy bars to test. Is that big enough?
No.
No. But it does say, assume the weights come from a normal distribution. So based on that, is it okay?
Yes.
Yes. Okay. But it is awfully small. Okay. I probably wouldn't like to do just 11, but you know, anyway. Shutting the machine down is expensive, so she uses alpha of 0.01. We've never used one of those. Okay. Okay, so assume the weights come from a normal distribution. Now, I'm going to ask Janie this question, and hopefully she's going to feel confident. With finding all the values, do you feel confident that you could find all the values?
Yes, but does that mean I have to find all the values?
Well, I would make you do it if we weren't out of time, but okay, so we're going to use our mu. So the question is, do you want a mu of 20.1 or 20? This is your label. We're going to go with the 20.1 because that's what the manufacturer calibrated the machine. You could also argue that that's what the label says, is 20 grams. But anyway, so n equals 11 is small, but since it's normally distributed, we're okay. X bar, you're going to have to find that from the data. Janie, do you feel that you could find the X bar easily?
Yes.
Okay. Now, so the sample mean is X bar is 20.3. Is there any standard deviation mentioned here?
No.
No. So we're going to have to find the standard deviation ourselves, which we found as S equals 0.64. I have a feeling that I rounded there and I probably shouldn't have. Okay, so if I give you raw data, you're going to have to figure out your S and your X bar yourself. Can everybody do that? Seth, can you do that on your calculator? Do you feel confident you can do that?
Yeah.
How confident are you?
99% confident.
99, I like that. That's a good number. Okay. We're using alpha's 0.01 in this case. Okay. Step
So I have
number
a question.
Okay.
So what is the difference when it's a normal distribution? Like, why is it okay that it's small? Like, we have a small sample size.
Because it's normal.
Yeah, okay, but like, what about a normal distribution makes that okay? Do you follow what my question
Back
is?
at the very beginning, the rules for the hypothesis test. So your
Okay.
sample must come from a simple random sample. By the way, does that say it came from a simple random sample? I forgot to check that. Oh, it didn't say it was random. So we don't know that this is random. That could be a bad thing. Okay, so we didn't say that it came from a random, so that would break one of the rules. Okay, the other rule is it must be independent. We didn't say it was independent, but we will assume it is. And the rule number 3 is it has to be normally distributed. Now, it should be n greater than 30, but smaller samples can be used if it's known to be normally distributed. So those are the 3 rules that we came up with at the beginning. So we might be breaking the rule because it didn't say it was random. It didn't say it was independent, but I think that's pretty safe to assume that it was independent. And we didn't check for outliers. The one thing that I have noticed about this book and other books is sometimes they just make these assumptions that everything's normal. And then you're like, wait a minute, there's a big outlier in there. You should take out the outliers if there is. But we're out of time, so we're not going to do that. But anyway, all right. Oh, that's weird, that one. So those are just kind of the ground rules for doing the test, okay? So actually there's so even though it's normal, it doesn't say that these are random. So technically we could be like, it's not random, we can't trust it. Okay, so this is quantitative. Our null and our alternative hypothesis mu is 20.1. Now, the question is, do I use a Z or a T on this one?
T, because we don't know the population standard deviation.
I like that you were confident in that. That was good. Okay, those are statements. That's good. Very well done. So this is a T, okay? So my T-score works out to be 1.036, okay? I've got 10 degrees of freedom. Now, normally I teach you how to do this in Excel, but the question is, can you do this on the chart, okay? So 10 degrees of freedom, we're on this line here. I got a T-score of 1.036. So here, I'll write that over here. T equals 1.036. Okay, we're on this line. I want you to tell me what is the p-value. And we're out of time, so I'll let anybody do it who knows.
Between 15 and 20%.
Between 15 and 20%. Because 1.0 is in between those two numbers. Does that make sense?
Mm-hmm.
Janie, are you good with that?
Yep.
Elise, are you good with that?
Yes.
How about you, Allie?
Yep.
Seth?
Yep.
Okay. You say you're all good. You better ace my quiz tomorrow. Okay? I hope I didn't I have to look at my quiz to make sure I didn't ask you to find the exact p-value. So just here, I will tell you this just for fun. On your formula sheet, oh, this isn't the formula sheet. On your formula sheet here, at the very bottom, these are the formulas you can use. You can do a t.dist. T.dist gives you left tail. T.dist.right tail, RT is right tail. T.dist gives you a two-tail probability. So if you want to, hopefully I didn't give you anything in the quiz or the homework that says find exact p-values, because you can't, but you could find them in Excel if you had to. But yeah, you'll be using the chart for everything. Okay. Oh, this was a two-sided test. I forgot about that. So now here's the tricky part. This is a two-tailed test. So we're looking, here, let me go back to here. So we're looking at 10 degrees of freedom. 1.0 is in between those two numbers, which means it's in between those two numbers, but that's just a one-tailed test. So you get to double that. So now, instead of it being between 15 and 20%, it's between 30 and 40%. Tricky. Okay. The exact p-value, because it's a two-tailed test, is 0.3246. Using the chart, you're going to put your p-value between 0.40 and 0.30. So that's the quiz. That's what I would ask you guys to do on the quiz or on the test. Okay. And the lease knows that that means we do not reject the null, right? Do you know that, Elise?
Yes.
Okay. And your conclusion, there is not enough evidence that the weights differ significantly from the label. So remember, we got 20.3, which is a little bit higher, but because our sample size is so small, we said, well, that's close enough. And plus, they're getting more candy. That would be a better thing than having less candy and getting sued because you got less candy. Okay? All right, so are you guys going to ace my quiz? We're going to go down the list. Elise, are you going to ace my quiz tomorrow?
I'll try.
Okay, Allie?
Yes.
Yes, I like that. Yes. We won't ask Bridger because he won't answer anyway. Easton?
Yes.
Yes. Janie?
Yes.
Oh, that was a question.
I'll try to.
Okay. Seth?
Yep.
Wes?
I'm batting in 89%, so the probability says I'm probably going to get a B.
So, all right. So you're only 75% confident you'll get an A?
Yeah.
All right. Okay. Well, I want you guys to do awesome. I know this is hard stuff. And I'll let you guys go. Do you guys have any questions for me before I let you go?
I do have one question on the candy bar one.
Okay.
How did we decide it was a two-tailed test?
Oh, that's a good question. I busted through that so fast. Let's see here. Punishment, quality control. So we didn't say whether we thought that the bars were high or low, did we?
Not that I remember.
So because we didn't know if they were higher or low, and the QC would probably, they wouldn't want to be too big or too small. If it's too big, we're losing money because we're giving the customers too much. And if it's too small, then we're going to get sued. So either way, it's bad.
Okay. I was just curious because it said that punishment for selling candy bars less than 20 grams was severe. So that made me think it was just one tail.
Well, I didn't think about that. You know what? You're right. You could argue that was one-tailed. I didn't think about that. You know what? You could argue that was a one-tailed test. Maybe I shouldn't have doubled that. You're right. Okay. You got me. You're right. I think I just wanted to show you how to do a two-tailed on there. But, well, I guess, yeah. I guess you would, yeah.
I mean, I can also see the argument that like quality control wouldn't want them to be too big, because if you're with the company, you don't want to spend more or like give out more.
Right.
But I just thought it was one-tailed because we're trying to avoid getting fined for having small can-do bars.
Let me say this also. Typically, when you're not taking a class, almost all of these tests are two-tailed tests, because that's just what the software defaults to. Plus, doubling it makes it a little bit more conservative, doubling the p-value. So, so if in doubt, I guess you should go with a two-tailed test. But this one, you're right. If you were to argue with me in class about this on if this was a test question, and say, well, I did that as a one-tailed because of that phrase, I would be like, oh, you're right. This one you could kind of argue it both ways, but yeah. Okay, any other questions? That was a good question. Any other questions? All righty then. Well, I will let you guys go. So ace my quiz.
So is the homework the 18 or the 20? Because you said that it was 18, but it's technically
I think I said 18, but it should be 20.
So the homework is 20.
Right. Did I publish 18?
Yeah, you published 18 when I was looking.
Yeah, don't worry about 18. Let's just go with 20.
Okay, sounds good. Thank you.
18's not bad, but 20's better.
All right.
Okay. Thanks. We'll see you guys later.